Hello, everybody. All right, so we're on our final unit, the end of grade 11 physics, and we're just going to talk about electricity for a little while. So, hopefully, you've done lesson one, and that's the go through all your previous knowledge, your grade 9 knowledge of electricity, the sort of static and current electricity problems that we did in grade 9. Hopefully, you've gone through that test that I put up on the internet, on the website there. Okay, so let's go a little bit more in depth now. So let's actually talk about some of the ideas in a more general sense and come up with some mathematical expressions to help us understand these ideas. Okay, so first off, let's go back to the big idea of grade 9 electricity, which is what we call the law of electric charges. And that was quite simply that if charges are opposite each other, then they're going to attract. And if they are alike, they're the same, positive, positive, negative, and negative, they're going to repel, fight each other. There's going to be a force against each other. And if they're the same, they're going to repel. If they're the opposite charge, they're going to attract. Now, that's a very heuristic idea. It doesn't give us any sense of how strong that force is or what direction. Well, we know that sort of the direction, but let's come up with a sort of quantitative way of thinking about this. Okay? Now, first of all, we're going to think about this as a little bit more generalized. Instead of the force between two charges, what is the force caused by one charge? So what we call an electric field. This is the idea that a positive charge here in this picture will produce what we call an electric field. It's a sort of a field of influence. Don't think of it like a sort of a force field or anything like that. It just gives us a generalized picture of round a charge, what sort of influence that charge will have on other charges. Now we're going to use for our test charge, for our other charges that we're going to think about, we're going to use positive. So when we have a positive charge, our positive test charge will repel it. Right? So positive and positive, they're the same charge, so they're going to repel each other. Right? So if I think about this now as what's the influence on this positive charge? They're going to be pushing away from each other. It's going to create a force. We're going to call this FQ. That's the Q we're going to represent as a charge. The symbol Q means charges. So there's going to be this force pushing outwards at this point. Now, if I move this positive test charge somewhere else, let's say I slide it all the way over here, there's still going to be a force pushing away, but it's going to be in a new direction. So what we call an electric field is all the directions. Imagine if I put that test charge everywhere, I will end up with this big picture of a whole bunch of arrows that represent all that influence of that positive charge. So we draw these field lines going outwards. Okay, and this is purely because we're assuming that our test charge is positive. That's just a convention. Now, what happens if it's negative? If it's negative, then our test charge will be pushing inward. Right? It'll be attracted because a positive and a negative are opposite. The law of electric charges tells us they're going to attract. So this will be pulling inwards. And again, if I move this somewhere else, there's going to be a new force pulling inwards again. And if I have it all around it, everywhere, imagine an infinite number of points around it, and at each point, this is a big idea. This is called a vector field, and and mathematically, it's a quite complex idea, well beyond the scope of this course. But it's a pretty straightforward idea. Think about here. Let's move. Let's go somewhere else. Let's go to here. This is a PHAT, these simulations you guys have played with. This is for charges and fields. So let's take a positive charge. I'll put this simulation, or this explorer, on the website. So let's take this positive charge. I'm going to drop it into the middle of my area here. And all of a sudden, it shows all these little dots. Every single little dot here represents a different point in space, and there's an arrow attributed to each one of these. So in this two-dimensional plane that I've broken up into this sort of grid, each point, they're going to calculate a force and give us an arrow. The brighter the arrow, the stronger the force, and the arrow direction tells us the direction of the force. And I can move this around. You can see as I move this around, it's continually changing my electric field, always pushing outwards from that positive. Because again, my test charge, the charge that I'm using to generate this, but to visualize this field, is a positive charge. And they use this, call this the sensor here. So as you can see, if I move this yellow dot around, this represents another positive charge. And as you can see, positive and positive, they repel. So the arrow's always going away from my positive charge. And I can move this around. As you can see, as I get closer and closer, it gets bigger and bigger. There's a strong force as I'm very close. And as I get farther and farther away, it gets smaller and smaller. Move it all the way around. You guys can play around with it. But it's the same idea with a negative. If I drop a negative on here, it's the same concept. It's just backwards, right? Because a positive charge is always going to be attracted to that negative charge, right? Our positive test charge, this yellow guy here, is going to be always attracted to our negative charge. And as our negative charge gets closer, the force gets bigger. As it goes away, it gets smaller. This is an inverse, right? And you guys can play with this as much as you like. Okay, let's take that sensor away. What happens though if there's two charges? What's going to happen if I have a positive and a negative? Now notice it's going out from the positive and into the negative. So we have these field lines generated. We call these if we connect all these arrows, we end up with these field lines out from plus into negative. Right? And we can do the same thing with two positives. Now the problem is these are always going to fight. Notice how these things are fighting, and if I bring them closer to each other, there's always going to be this spot where these field lines are going to be fighting each other. Field lines can't cross. Okay? Field lines can never cross each other. So these positives, when they get closer and closer to each other, this is where the repulsion comes from. Because these field lines are always fighting each other. If now I replace this with a negative, you can see the field lines are going into each other and we have an attraction. Right? This gives us a sense of why the law of electric charges works the way it does. Right? And we can do multiple. We can play around here. We can add a whole bunch of these guys, and we can watch these field lines. You can see they tend always out from the plus and into the negative. Right? So again, repulsion occurs because those field lines can never cross. They're always going to be fighting each other. It looks as though they're crossing, but they're actually turning up that way. Okay, these are always going to fight. They're never going to be able to cross. It's difficult in this picture to see that, but they're always going to be going that way. And attraction is the opposite. They're always going to go out plus into the negative. And these field lines, since they're flowing nicely, they're going to cause these two charged particles to attract. These are going to attract, and these are going to repel. All right, so already now we have this idea of these field lines and these vector fields of this electric field generated by these charges. We've come up with the law of electric charges that we already have. Now, what about the strength? Now, if we would go back to Unit 2, I think? Yeah, universal gravity was in Unit 2. Right? We came up with this formula. We derived a formula that represents the strength of an electric field. So where did these terms come from in this equation, right? The force of gravity is G, so this constant G times mass 1 times mass 2 divided by some distance squared. So where did they come from? Remember that the force was proportional to masses, right? So then the force and the mass are both in numerators, right? So the force and the mass are proportional. So they just multiply the masses. So the bigger the masses, the more force. That made sense, right? And we needed a constant to make it equal. We made proportionalities into an equation. And then we had divided by r squared. So it was inverse, but it was inverse square. And if we recall, this came from this idea of a sphere and the surface area of a sphere. So every time we increase by our distance r, so we go from r, 2r to 3r, we're increasing the area by a square. So here we have 1a, now we have 4 a's, and here we have 9 a's, 16, 25, and so on and so forth. So every time we go farther away, the same amount of force. So here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 force lines, let's say, going through that area. And then now we have to reduce that. Now there's only 3 or 2, right, through each of the areas. And here there's only 1 going through each area. So we're reducing the force since the force has to be acting on a much larger area. Right? So, and this comes from the fact that the charge influences spherically symmetric. The influence of the charge doesn't care where you are on that sphere. Right? This makes sense. It wouldn't matter where I am. If I'm at a distance r away, it wouldn't matter that I'm on the left side or the right side or the top or the bottom or anywhere on that sphere. I'm going to have the same influence. So because these forces, just like the gravity, electrical field strength, they're all spherically symmetric, their equations end up being very similar. And we actually come up with what we call Coulombs Law, which has a very, very similar structure to our equation. Again, we have, the larger the charges, the larger the force. So we're going to multiply the two charges on the numerator, and we're dividing by r squared. So it's it's an inverse square. And then to make everything equal, we need a constant. And this constant here is 9 times 10 to the 9 Newton meters squared per Coulomb squared. What is a Coulomb? Now we're going to use this unit to measure these Q's, these charges. We're going to use this unit called a Coulomb. And we'll discuss what that means exactly in a minute. Okay, so just a quick example. Let's use this equation. If I have 2 electrons and they are 10 to the negative 10 meters, that's another name for that is called an angstrom. This is a unit used to measure atomic distance. Atoms are in this order size. Atoms typically are in the 10 to the negative 10 meter size. So that makes sense that we could have electrons that are this far apart. What's the field strength going to be between them? So I can replace everything in the equation. Now we're going to use here for coulombs, for the charge, this number here is 1.609 times 10 to the negative 19 coulombs. That is the charge. That's what we call the elementary charge. That's the smallest amount of charge that's possible on a free particle in the universe. It's the elementary charge. And that represents what the charge on one electron is. And since we have 2, it'll be 1.9 times 10 to the 19 times 1.9 times 10 to the 19. So I'm just going to square it. And then I'm going to divide by the distance, 10 to the negative 10 meters squared. And that works out to 2.3 times 10 to the negative 8 newton. So really not very much charge. However, the charge is a lot stronger than gravity between. Okay, don't worry about that. So we can use this equation to quite simply put these numbers in, square them, work them all out, and we'll come up with an equation. And notice this, the units work out because the Coulomb squared cancels with the Coulomb squared here. Then I have meters squared divided by meters squared, and we're left with just Newton. Okay? So that's the strength. And so 1 Coulomb is the inverse of this number. If I take 1.9 times, 1.9 times 10 to the negative 19 coulombs, 1 Coulomb is the inverse of this. 1 divided by this number represents Coulomb. Or here, it's 6.24 times 10 to the 18 electron. Now, let's move on to electric current. So current, when I have a current through something, an electric, so through a wire or something, the current tells us how much charge is traveling through that conductor in 1 second. So it's the rate of change with respect to time of charge. So I is the number of charges, Q, divided by our time interval. And we're using 1 second. So we're using our typical international SI units. We define this current as what we call an amp, or an ampere, named after the French physicist Ampere. We shorten that down to an amp. You probably heard that. The plugs in your house are typically 15 amps. Maybe the dryer or stove, they could be 30 or 40 amps, but typical house circuits, the wall plugs, they're 15 amp circuits. And we define that 1 amp to be 1 Coulomb per second. So that's 6.24 times 10 to the 18 electrons per second. Now remember, this was all done in the 19th century, so 1800s. And that means that the ideas that we're coming up with here, these concept of electricity, predate the electron. The electron was discovered in the 20th century, right, by Thomson. Was it Thomson? No, it was who was it? I forget now. No, it was Thomson, actually. J.J. Thomson, right? So he discovered the electron in the early 20th century. So we defined a Coulomb well before that. So we have to kind of go backwards and say that a Coulomb is 6.24 times 10 to the 18 electron. So that's our current, the idea of flowing electrons. We have batteries that push out electrons. There's an electric potential voltage that pushes on the electrons, and they end up traveling through our circuit. All right, so we have this idea of of a current traveling through a conductor. So we have to be very careful, though. Again, all this stuff was done in the 19th century, so there was no electron. So when they decided which way current would flow, they had a choice. They could have chosen, positive to negative, negative to positive. It was completely arbitrary. And they decided, well, Benjamin Franklin decided that current, or this electricity, this flow of electricity, would travel from the positive of the battery, let's say, to the negative. And since they thought that positive charges were the actual charges that were moving. Now, they're wrong, right? Because electrons exist. Electrons move. So we have to be careful. When we talk about current, when we say the direction of current, that's from the positive to the negative. We call that conventional current. What that means is that the electrons are traveling the opposite direction. Now, you got to ask yourself, okay, so why didn't we just drop the idea of conventional current? And it's because all the directions of vectors and magnetic fields and all the rest of it were all based on this idea. And for us to change everything actually will cause more problems. So instead, we're just going to leave it as saying that conventional current goes from positive to the negative. And then we're going to use that idea. You'll see in lesson 4, I think. We'll be using the concept of conventional current to define some directions of magnetic fields. But remember that the electrons are actually traveling the opposite direction. Okay, the electrons are negative, so they're being repelled from the negative side of the battery, go through the light bulb, and are being attracted to the positive. Okay, that's the direction the electrons flow. However, we say that the current travels out the positive and into the negative. Now, alternating versus direct current. When we have direct current, that means that the potential, the push out of the battery, is the same all the time. So, for example, your cell phone batteries, something like 3.8 volts, constantly. It does vary slightly due to the amount of charge you have left in it. That's actually how your phone knows how much charge is left in it. It actually measures the voltage, and there's actually it's calibrated to know sort of what the voltage profile over use should look like, and they calibrate how much charge there should be left. But over a short enough time scale, that voltage will stay constant. And because that voltage is constant, the amount of stuff that I'm pushing out of the battery is the same. It means that the current through the battery is also the same. So in direct current, the voltage and current just stay the same the whole time. Alternating current, the wall plug current, actually changes rapidly. We in Canada have a 60 hertz current, which means that the voltage goes from positive 120 volts down to negative 120 volts and then back up again 60 times in 1 second. Okay, so there's a 60 hertz current that goes up and down, and it varies when we say sinusoidally. It's a nice sine wave. We hope it's a sine wave. Typically, it's actually a bit noisy, but don't worry about that typically. That means that when it's pushing in the positive direction, the voltage, then it's also going to push the current in the positive direction, and then the electrons are actually going to change direction. They're going to flip and start going the opposite way. The current will now be going in the negative direction while the voltage is negative. So in your wall plug, the electrons are actually going back and forth rapidly, and it's that rapid back and forth that actually is what produces our the power that we get out of our wall plug. Okay, typically things we plug into it, they use something called a rectifying circuit to make it always positive or make it closer to a direct current. That's what your cell phone charger, that little wall plug, it takes that 120 volt up and down here and turns it into approximately 5 volt, approximately DC. It's not exact, but it does it as well as it can to produce a constant 5 volts. That's what USB is. Constant 5 volt output. Some of the fast chargers do like 9 volts, but let's not worry about that. Okay, so we have alternating, which means it keeps changing back and forth 60 times a second, and direct, which is just a constant flow. Okay, so that's all we're going to talk about today, just as our introductory new ideas about electricity. So we talked about Coulombs Law, we talked about electric fields, and we talked about current. Actually, quite a lot in this first lesson. Remember, electric fields are out from positives into negatives. Strength is, again, an inverse square. So we end up with that Coulombs Law equation, K, Q1, Q2, all R squared. And current is the flow of electrons measured in amps, which is a Coulomb per second. Okay, so these questions here are basically doing some calculations using that I equals Q over T equation. And that'll be it for lesson 2 here in unit 5. All right, so again, I hope you guys are all well, and be talking to you later.